All right, let's go ahead and finish up our book learning exercise. So I talked about microkernel. Mac OS X is kind of a microkernel as well. Oh, Mac is based off of BSD and some of Mach. They kind of put the two together. BSD is another Unix derivative. Think of it as another version of Linux that someone else wrote. A group of people wrote. The trick, BSD is under the BSD license, Linux is under the GPL license. So they kind of combined the two and made Mac OS X. So I talked a little bit about modules. They have some sort of kernel module. It's an O approach. That doesn't mean they're using objects. Really, they're just modularizing the different components. So for example, Solaris, they'll have a module for each one of these. It's still a monolithic kernel, but you can plug and play the different modules, and it can load the module depending on what piece of hardware you have. Okay, virtual machines. We're all used to this, aren't we? VMs, good. Depending on which VM you're using, you have a host that creates an illusion of a process, and then a guest that provides a copy of the underlying computer. This is actually a very old well, not very old. It's somewhat old, 72. The idea is they want to consolidate many low resource usage into a big one. Really, you had a huge mainframe. You'd rather have one huge mainframe as opposed to everyone trying to run their own mainframe. And this was back 72. Not everyone could afford a computer to run on their desk. One, it wouldn't fit, and two, the desk would probably get crushed. But, so you had to do it a little differently. You'd have one giant mainframe down in something that was probably larger than the size of your garage, and then you would connect to it.
IBM 360.
360 was the first. Was a big one. That was a big one.
But your first desktop computers didn't come out until like 1980.
Yeah, the mini computers.
Like the TRS-88.
All right, virtual machines. Wow, that did not come out well. Left is what normally you're looking at, but on the right is your virtual machine. You'd have your hardware, virtual machine implementation, maybe a little something on top, and then you have your kernel for each terminal or each program. Left is what's normal, right is what it turns into. Bringing it forward to modern, you have VirtualBox. You might be running virtualized one version of Windows, virtualized Linux, virtualized something else as well, and they're all running on your one machine. Same idea. Pair virtualization. Presents guests with systems similar but not identical to hub. So this is if you want to emulate certain devices. This is what's normally done. VirtualBox will just emulate one single device that most operating systems can do. Standard network card, standard graphics card, et cetera, and then it'll translate it in the back end for you, as opposed to true virtualization where it pipes it through.
Is this like then? Is that how you do your apps for phones and such when you do app development, and you want to check it out, run it? Let's say the Oracle when you're doing your apps, and you tell it, okay, I'm going to be running on this particular type of Android or this different type of Android.
So in that situation, you're on the right track, but that one is actually emulation. In general, that is emulation.
Emulation.
Because, and the reason for that, what? Yeah.
Because the chippy things are different.
The chippy things are different. Thanks. I love your explanation. It's like you know it all. We gotta say the right words.
The chippy things.
The architecture, the instruction set architecture is different because these are x86 machines, and you have to emulate ARM, which means it has to emulate ARM instructions, and you can't really virtualize that.
Emulate, not virtualize.
Emulating. The difference is emulating is you're taking the instruction, and then you're actually manipulating how it should behave under a system and sending it back.
Well, I thought that
virtualization.
Pair virtualization.
Okay, yeah. Hold on. I know where you're going. Let me explain the whole thing. So that's emulation. True virtualization is where you get your program, you divide some piece of hardware for it, and then you pretty much let it directly communicate to it. You have a layer to intercept certain things, but you're going directly to the hardware. You see the hardware yourself. You're running the instructions on the CPU itself. Paravirtualization is you'll still be running the CPU instruction set, but instead of communicating directly with your network card, the virtualization software will emulate. So this is where it gets a little hybrid. Emulate a standard standard network card, and you communicate with that, and then that just does a translation directly to your network card. So paravirtualization, there's a kind of a layer. True emulation, everything is basically a user process. You're never really going into the hardware, so to speak. So I know it's a little hard to understand, but that's what's going on. All right, we're not going to do Solaris 10, but VMware, this is what you're used to. With VirtualBox, you have your host Linux OS running on top of hardware, and then maybe a virtualization where you can do FreeBSD, Windows NT, Windows XP, or whatever you want. All right, the JVM is also a virtual machine, although it's a little trickier. Class files, class loader, interpreter, then runs on your host system. But it's emulating, or it's a paravirtualization. It's virtualized Java machine. Because the interpreter takes your class code and translates it to something that runs directly on your machine. So this is more of a paravirtualization environment, as opposed to a pure emulation environment or simulation. Okay, debugging. Hopefully, we've all experienced bugs, I hope. The OS actually does a good job of generating log files. It just does a bad job of letting you find them. They're usually hidden.
Or explaining them.
What?
Or explaining them sometimes.
Or explaining them, that's true. It used to be programs would do core dumps. When your program crashed, seg fault, it would give you a core and you could inspect the memory and figure out what's going on. By default, that's been turned off because too many systems were being filled with core dumps. But you can turn that back on if you want to. People write bad code, it keeps dumping the core, your hard drive fills up, etc., etc. You're giving me the what's going on look.
Couldn't you just write one core dump for the latest one?
You timestamp the core dump so you know which core dump you're looking at, and so that would be a unique file each time.
The big machines, the IBM 370, 360s, they used to, their core dump was actually, in order to be taken to the memory, they would go and print it out. It would print out.
It would be a printout? Oh,
It would be a
funny.
printout.
Oh, that would be funny. Oh,
Now-
that must be
now we had to
terrible
go back
to
and
read.
look through it.
That would be terrible to read. Oh. Oh. Yeah, performance tuning can optimize. If you don't know this already, very important law, debugging is twice as hard. Actually, it's at least twice as hard as writing the code in the first place. Therefore, write the code as cleverly as possible, because you, by definition, are not smart enough to debug it. All right. Again, make sure you just write it first. Just write it correctly the first time, guys. There are programs to trace, debug trace. They kind of look like something like this. We don't need to go. This actually tells you all the system calls. Knows ioctl, running a couple other system calls as they come back down. Bootstrapping. This should be near the end. Oh my goodness, we've gone through a lot of slides. Computer turns on bootstrapping. We did this. It's like grub. You select which operating system you want, it loads it into memory, and then it hits go. Sometimes it's stored in ROM. Sometimes it could also be located in the hard drive. Bootstrap loader, smallest piece of code, loads it all in, boot blocks, fifth location. Your hard drive usually has something called the master boot record, that's where you write the first piece of code that's executed when your system points to a hard drive. So it loads that in. That's usually your bootloader, grub. And then your bootloader may load something from the hard drive when you select which operating system you want.
It used to be, what, the first few, whatever, you knew you started from 0, 0.
Yeah, there's a certain size to it.
Yeah.
Now, advanced, since that side, things get more complicated. There's another version. It's called I cannot remember what it's named anymore. But it goes. You take your master boot record, and then you can read more from it as well. It's your master boot record basically points to some part of the hard drive, and then that's where your bootstrap program is loaded into memory. Yeah. Just taking it one step further. Great. End of chapter 2. All right. Chapter 3, we're going to start talking more about processes and intercommunications, and that'll be great because we can start doing some code and actually playing with these different processes to see what they do. But that's it for chapter 2. Any questions before we go talk about the bookwork real quick? All right.